Thank you for the presentation. I'm Pablo Vizcaino. I work at the Barcelona Supercomputing Center, and I'm doing my PhD with the Universitat Politècnica de Catalunya. In my PhD, one of my works is the RAVE, which is the RISC-V analyzer of vector executions, which is a QEMU tracing plugin. So a little bit of context on this. You may have heard that the RBB, or the RISC-V vector extension, is the RISC-V approach for high-performance computing to get real power. And it has two main particularities. One of it is that the maximum vector length is not defined by the specification. It's up to each implementation to decide how long your vectors are. The second special thing about it is that the vector length is variable during the runtime. So you can have, for example, one iteration with this vector length, another one with this vector length, and another iteration with another shorter vector length. OK, so with that clear, one of the first implementations of this RBB for HPC is the European Processor Initiative, or EPI for short. One of the works of that project is the REA. It is an ARM-based general-purpose CPU, but we are going to focus on the EPAC chip. The EPAC is the European Processor Accelerator, and it contains many tiles. One of them is the BEC one, which is also RISC-V, like the others. And this is the one that has the CPU and the vector processing unit. If you want to know more about this, you can come to the BSC booth. We have a prototype, and we had a demo an hour or two ago. But you can come to the booth, and we will do the demo for you also. The special thing about the EPAC is that it has very, very long vectors. Here, you may be used to Intel AVX 512, which has 512 bits per vector. This is 8 double precision elements. With the EPAC chip, we are on 256 double precision elements per instruction, which is not only bigger, but it's a complete different philosophy of short and long vectors. So let me jump to the demo. So imagine you are an HPC developer, and you have a code that might look like this. You have a loop of time steps. Each of them calls a step function. And inside this step function, you have, for example, a pressures array, a temperature. You do different kinds of computations that you can find on normal HPC codes. If you are lucky enough, you might have access to a RISC-V machine where you can compile your code for RISC-V, which will compile. You can execute it, no problem. But what happens when you start adding vector instructions to your code? If you do that by adding some flags to your compilation to vectorize the loops, the compiler will tell you, OK, I'm vectorizing this loop, I'm not vectorizing this other loop, and so on. But if you try to execute this binary, what will happen? Illegal instruction. Because most commercially available CPUs, in this case, this is Unmatched Sci-5 board. It has many extensions, but not the vector one. It's still hard to get your hands on hardware that has the vector extension. What's even worse, you might not even have access to a RISC-V machine. So this is my laptop. This is an Intel laptop. If you try to run your binary there, of course, you cannot do it because this is a RISC-V binary on an Intel machine. So what do you do when you don't have access to the B extension, or you don't have access to a RISC-V machine? You can do simulations. What we do in this presentation is use QEMU plus a plugin that we created, which is called RAVE, which is the RISC-V analyzer of vector executions, to be able to run your code. So again, in my laptop, I can use RAVE, and the code runs. I can run the vectorized code. Again, it runs. But the most important part is that you can trace your application and analyze it. So for example, if I put here RAVE print report, I get, at the end of the execution, a report which counts the number of instructions that are executed, and how many of those are vector. You can see, for example, what is the average vector length, because as I explained at the beginning, the vector length can change during the execution. So this is telling you are on average using 72 elements per instruction. Our maximum was 256, so this might not be good news. You can count how many of those are arithmetic, memory, and so on. The next thing that you can do with RAVE is to instrument your code to get more fine-grained details of your application. For example, you can enclose your regions of interest in this RAVE event and value. For example, here I'm putting the value 3, which is corresponding to volumes, because this loop is computing the volumes. If I execute this instrumented version, what you get is much more data. For example, let me go here. This is the region for the temperatures part of the code. Here you can see that 7% of the instructions are vector, which is not great news. Also, it's not too low, but it's not too high. The vector length is even worse than the average of the whole application. It's 32 elements out of 256. And half of them are arithmetic, a little bit more than half memory, and so on. What else can you do with RAVE? You can also generate traces. So here you see a sequence of the different code phases that are simulated. You can also get this kind of sequence of instructions. If you zoom in, what you get are two distinct rows, one for scalar instructions, one for vector instructions. And you can see, for example, that you're doing scalar work. Then with that color, you set the vector length to whatever value you want. Then there's a vector load, some scalar, vector load, scalar. This is arithmetic vector instructions. And you can do this kind of fine-grained analysis of how the compiler is behaving and how your code is being vectorized. Also, you can get this kind of tables where you can count the number of scalar and vector instructions per each phase. You can also get this in relative numbers, so it's a 7% of vectorization. We saw that before on the report, on the demo. And what you can do then is try to look at the compiler output, see why are some, because if you see here, there are two phases that are not being vectorized. That's the kind of insight that this plugin can give you. And then you can see, for example, the compiler is not vectorizing one phase because there's a call instruction inside the phase. This one is not being vectorized because the compiler cannot identify the right bounds. This is related with pointers. This is part of a bigger demo, but mainly we fix these issues. We trace again. Now the volumes phase is vectorized. Pressures is divided into two phases, one that has the function call, another that doesn't have the function call. But this is just to give you the idea of the kind of insight that you can get with RAVE and the kind of changes that you can do to your code to increase the vectorization. Another thing that you can do is plot the vector length and how it evolves through the code. So maximum 16,000 bits, that's the epoch maximum, minimum 0, of course. You can see that we are doing kind of bad on this white phase. We are on the 32, or in this case, this is bits, so 2,048 bits. And these ones are still not at 16,000, which is the maximum of the machine. In short, normally on codes, you can find this kind of accesses or this kind of loops. And the auto-vectorizer is normally limited to the size of your loops. In this case, m is a very small value. So what you can do is collapse the loops into a single one. Your loops are now bigger. You can take advantage of the very long vector length. Also, for the temperatures phase, this is the one that has a very low vector length. There's this kind of blocking structure that you can find on many HPC codes. What you can do normally is make the blocks bigger, so you take advantage of the long vector length. So we did these changes. We get a RAVE trace again, and you can see that now this line is higher than before. These numbers are also higher than before. This is very close to 16,000. And this is a little bit smaller, but still better than before. Finally, other kind of tables that you can get with this tracing plugin, you can count each type of instruction, and so you can detect some anomalies. For example, I don't know if you are familiar with the RISC-V vector extension, but there are some widening instructions and slide down instructions. These are normally high latency. It depends on the implementation, but they can be high latency. And they are not related with how your code is written. They are not actual computation or load or store. It's normally the compiler not being able to do a good job. In this case, they are related with mixing data types in your code. You can solve this and you can remove them. But this is, again, the kind of insight that you can get with this plugin. I want to end my presentation by quantifying the use of this plugin. So if you come to our booth, you will see that we have the actual hardware. We are lucky enough to be able to run vectors on RISC-V. And what you see on this plot on the left is the different versions that have been improved only using simulation and then tested on the actual hardware to see that the changes that we do on simulation also benefit the real-time execution. This is just the same plot, but in a speed up. So I want to thank the funding for the API project, of course, and insist that please come visit us at the BSC booth so you can see this in action yourself. Thank you very much.